Right now, as you watch this video, there is something moving through our solar system, something ancient, something cold, something that has been traveling through the darkness of space for longer than human civilization has existed, and in a few decades, it will be gone forever. Not just gone from our sky, gone from our solar system entirely, drifting out into the galaxy, alone, silent, carrying within it the frozen secrets of how our world was born. Its name is Comet C 2024 E1. Scientists also call it Wierzchos. And what this comet is doing right now, what it is telling us, and where it is going, is one of the most quietly remarkable stories in modern astronomy. I have been watching the sky for a long time. I have seen comets come and go. I have watched telescopes get bigger and sharper. I have seen discoveries that changed what we thought we knew about the universe. But every now and then, something comes along that makes you stop. Something that reminds you just how vast and strange and humbling the cosmos really is. This comet is one of those things. So let me tell you its story. From the beginning, space is full of things we cannot see. Most of the solar system is invisible to us on any given night. We see the moon, we see the planets, if we know where to look. On a clear night, far from city lights, we see the stars. But stretching out far beyond the planets, far beyond even the most distant known objects in our solar system, there is a region we have never directly visited, never photographed up close, and can barely detect even with our most powerful instruments. It is called the Oort Cloud. The Oort Cloud is not a cloud in the way we usually picture one. It is not dense or visible. It is an enormous, roughly spherical shell of icy bodies that surrounds the solar system at an almost incomprehensible distance. The outer edge of the Oort Cloud may extend nearly a quarter of the way to the nearest star. Think about that for a moment, a quarter of the way to the nearest star. And it is filled with billions, possibly trillions, of small icy objects that have been sitting out there, mostly undisturbed, for nearly 4.5 billion years. These objects formed when the solar system was young. They were part of the same swirling disk of gas and dust that eventually became the planets, the moons, the asteroids, everything we know. But these particular objects were thrown outward by the gravity of the giant planets. As those planets grew and settled into their orbits, Jupiter alone, with its enormous mass, scattered countless icy bodies outward over the early history of the solar system. Many of them ended up in the Oort Cloud, where they have sat ever since, frozen, preserved, changed by almost nothing except the slow occasional tug of a passing star or the weak gravitational rhythm of the galaxy itself. For most of these objects, that is the end of the story. They sit out there in the cold and the dark for billions of years, and nothing ever happens to them. We never know they exist, we never see them, but sometimes, very rarely, something disturbs one of them. A nearby star passes a little too close, a ripple in the galaxy's gravity reaches in and nudges one of these frozen travelers. And it starts to fall. Not quickly, not dramatically, slowly, over thousands or even millions of years, it begins a long, curving path inward toward the sun. It travels through the outer solar system, past regions so remote that even sunlight barely reaches there. It keeps falling inward, year after year, century after century. And then one day, it gets close enough that someone on Earth looks up at the right part of the sky with the right instrument, and they see it. A faint, moving point of light, a visitor from the deepest reaches of the solar system. That is exactly what happened with Comet Wierzchos. In March of 2024, a Polish astronomer named Kasper Wierzchos was conducting observations using equipment at the Mount Lemmon Observatory in Arizona. This is one of many facilities involved in ongoing sky surveys designed to detect faint, moving objects. Asteroids, comets, anything that might be worth tracking. Most nights, these surveys find ordinary objects, objects that have been seen before, or that behave in familiar ways. But on this particular occasion, something different appeared in the data. A faint, distant point of light that was moving, and when astronomers began calculating where it had come from and where it was going, it became clear that this was something worth paying close attention to. Follow-up observations confirmed it. This was a comet, and it was arriving from the Oort Cloud. It had been falling toward the inner solar system for an extraordinarily long time. Based on its trajectory, this appeared to be its first close approach to the sun in possibly millions of years. Perhaps even its very first. an object that had spent most of the age of the universe in frozen silence and was now finally making its long journey to the light. As the comet moved closer to the sun over the following months, it began to do what comets do. The frozen surface started to warm. Ices that had been locked up for billions of years began to sublimate, transforming directly from solid to gas. That gas, along with dust particles carried with it, began streaming away from the comet's nucleus, forming the characteristic hazy envelope called the coma, and the long tail that gives comets their familiar dramatic appearance. And then something caught the attention of the people photographing it. The comet was green, not a vivid electric green, more like a soft, pale emerald glow surrounding the comet's head. It was subtle but unmistakable in photographs taken under dark skies, and it was unusual enough to generate real excitement among astrophotographers and astronomers alike. This green color in comets is not unheard of, but it is not common either. For a long time, the explanation that was commonly offered was that it came from a molecule called dicarbon, two carbon atoms bonded together, being excited by ultraviolet light from the sun and emitting that characteristic green wavelength. More recent research has offered some refinements to that explanation, suggesting that other carbon-bearing molecules may also play a role, but the general picture is consistent. When sunlight interacts with certain carbon-rich molecules in the comet's coma, it can produce that striking green glow. The presence of this color tells scientists something important. It suggests that this comet carries significant quantities of carbon-bearing compounds, and that, as we will see, turns out to be deeply interesting for reasons that go well beyond the visual spectacle. The comet reached its closest point to the sun, what astronomers call perihelion, in late January of 2026. And then in mid-February, just around the time this video is reaching you, it made its closest approach to Earth. The distance at that point was roughly comparable to the distance between the Earth and the Sun. In cosmic terms, that is not particularly close. The comet was never going to be a naked-eye spectacle for most people, but for observers with binoculars or a small telescope under a reasonably dark sky, it was a clear and rewarding target. A soft, faintly glowing smudge moving slowly against the stars, carrying within it materials that have been frozen since before Earth existed. But the visual observation, as lovely as it was, is only a small part of what makes this comet important. The real significance came from what happened when scientists turned the James Webb Space Telescope toward it. The James Webb Space Telescope is the most powerful astronomical instrument ever launched into space. Its primary mirror is over 6 meters across. It observes primarily in infrared light, meaning it can detect heat signatures and molecular fingerprints that are completely invisible to ordinary telescopes. Since it began science operations, it has produced extraordinary results in virtually every area of astronomy it has been pointed at. And when its operators decided to observe Comet Wierzchos, they found something that generated immediate scientific interest. The telescope detected significant amounts of carbon dioxide in the comet's coma. Now, that might sound straightforward. Carbon dioxide is a common molecule, we encounter it every day. But in the context of comet science, this detection carries real meaning. Most comets are largely made of water ice. When a comet gets close enough to the sun, the water ice warms, sublimates, and drives much of the activity we see. The development of the coma, the tail, the outgassing, water ice is the dominant engine of most cometary activity in the inner solar system. But water requires a certain amount of heat before it starts to significantly sublimate. It needs the comet to be at a certain distance from the sun before it really gets going. Carbon dioxide is different. CO2 is far more volatile than water. It begins to sublimate at much lower temperatures, meaning it can drive cometary activity even when an object is still quite far from the sun, in the colder outer reaches of the solar system. For astronomers studying how comets evolve and what they are made of, detecting carbon dioxide helps paint a much more complete picture of the object's composition and behavior. But there is something deeper here. These long-period comets, arriving from the Oort Cloud, are considered among the most pristine objects in the solar system. They have been out there in the cold and the dark for billions of years, largely isolated from the processes that have reshaped the inner solar system. The planets have been through enormous changes. The asteroids have been battered and heated and altered by collisions and by proximity to the sun. Even most comets that visit the inner solar system regularly have been gradually depleted and changed by repeated passages near the Sun. But an Oort Cloud visitor like Wierzchos, possibly making its first close approach to the Sun, may be carrying the original, unmodified chemistry of the early solar system. It is, in a very real sense, a time capsule. And the James Webb Space Telescope gave us the ability to open that capsule, at least partially, and read some of what is written inside. The carbon dioxide detection helps scientists refine their models of what the outer solar system looked like in its early history. It contributes to the broader effort to understand what materials were available when the solar system formed and where those materials were distributed. These are not small questions. They connect directly to some of the biggest puzzles in planetary science, including questions about how the ingredients necessary for life were distributed throughout the early solar system and how they might have reached Earth. But there is still another layer to the story of this comet, and it may be the most thought-provoking of all. When astronomers carefully analyzed the trajectory of Comet Wierzchos, they found something that immediately set it apart from the vast majority of comets we observe. Its orbit is hyperbolic. Most comets travel on elliptical orbits. An ellipse is a closed curve, like an elongated circle. A comet on an elliptical orbit, no matter how long that orbit takes, will eventually complete it and return. Halley's Comet comes back roughly every 75 years. Some long-period comets have orbital periods of thousands or even millions of years. But if the orbit is elliptical, the comet is gravitationally bound to the Sun. It will come back. A hyperbolic orbit is different in a fundamental way. A hyperbola is an open curve. A comet traveling on a hyperbolic orbit is not going to loop back around. It is going to pass through the inner solar system, swing around the Sun, and then continue outward indefinitely. The Sun's gravity will slow it, but not stop it. It will keep moving away from the Sun for the rest of time. There are different ways an object can end up on a hyperbolic trajectory. It might have received a gravitational kick from a planet during its journey inward, or during its close approach. It might have been given just enough of a push that it crossed the threshold from a very elongated elliptical orbit to a slightly hyperbolic one. Or it might have come in on a trajectory that was already marginally hyperbolic, meaning it was never truly bound to the solar system to begin with. For Comet Wierzchos, current analysis suggests that gravitational interactions during this solar passage are expected to send it outward on a path from which it will not return. It may take many decades before it fully escapes the influence of the outer solar system. It might be a century or more, but the trajectory points in one direction, and that direction is out, into interstellar space, into the galaxy. This is the moment where I want you to really pause and think about what that means. This object formed in our solar system. It formed from the same cloud of gas and dust that gave rise to the Sun and every planet orbiting it. For nearly 4.5 billion years, it has been part of this solar system. Sitting out in the Oort Cloud, frozen and silent, belonging to this small corner of the Milky Way. And now, in this century, in this decade, in this year, it is leaving. It will drift outward past the planets, past the outer solar system, past the Oort Cloud itself. And then it will be in interstellar space, in the vast emptiness between the stars. It will travel through that emptiness for millions of years, possibly for billions of years. It might eventually pass near another star. It might be captured by another star's gravity and spend the rest of its existence in a completely different solar system. Or it might just drift forever, alone in the dark, carrying its frozen cargo of materials from our solar system's ancient past, never to be seen or touched or studied again. When you think about it that way, this comet's journey through our inner solar system right now is a kind of farewell. The only close encounter it will ever have with the warmth of the Sun. The only time it will ever be visible to any eyes, if there are eyes anywhere, before it disappears into the dark forever. That is not a small thing. It also connects this comet to a conversation that has become increasingly important in astronomy over the past several years. The conversation about interstellar objects. In 2017, astronomers detected an object passing through the solar system called Oumuamua. It moved fast, it was small, and its trajectory was clearly hyperbolic. It came from outside the solar system, it came from interstellar space, it passed through the inner solar system and continued outward. It was the first confirmed interstellar object ever detected. It generated enormous excitement, enormous debate, and some wild speculation about what it actually was. Most scientists believe it was a naturally occurring fragment of some kind, perhaps a piece of an icy body from another star system, but its passage raised a profound question. If objects from other star systems can visit ours, how often does that happen? And what does it mean? Then in 2019, a comet called Borisov was detected on an interstellar trajectory. Unlike Oumuamua, which was point-like and showed no signs of the outgassing activity we associate with comets, Borisov behaved exactly like a comet. It developed a coma and a tail. It was studied in detail. And its composition, as far as astronomers could determine, was remarkably similar to comets from our own solar system, an ordinary-seeming comet that had been wandering through interstellar space and happened to pass through our neighborhood. And then, just last year, astronomers detected a third interstellar visitor, designated 3I/Atlas, another object on a hyperbolic trajectory arriving from outside the solar system, providing yet another opportunity to study material from beyond our stellar neighborhood. These three objects, Oumuamua, Borisov, and 3I/Atlas, are interstellar visitors to our solar system. Comet Wierzchos is something different, but related. It is a solar system native that is about to become an interstellar traveler itself. It is going to leave. And that means our solar system is not just receiving visitors, it is also sending them out. This is something that has been understood theoretically for decades. The Oort Cloud itself is believed to have been partially populated by objects from other star systems that were captured early in the solar system's history, just as our Sun may have ejected countless objects into interstellar space over its lifetime. The exchange of material between stellar systems is not rare. Over billions of years, it is inevitable. Stars pass close enough to each other to gravitationally interact. Objects get scattered. The galaxy is littered with frozen debris from ancient solar systems. Comet Wierzchos lets us watch this process in real time, or at least on a time scale that we can actually comprehend and measure. It is not going to complete its transition to interstellar space in our lifetimes, but we can see the trajectory, we can measure the path, we know where it is going, and we got to observe it up close with the most powerful telescope ever built while it was still here. There is another aspect of this story that deserves attention, the role that new and improving technology is playing in our ability to find and study objects like this one. The Mount Lemmon Observatory, where Wierzchos made the discovery, is part of a network of automated sky surveys that scan large portions of the sky on a regular basis, looking for anything that moves or changes. These surveys have become increasingly sophisticated and productive over the past 2 decades. They have dramatically increased the rate at which astronomers discover comets, asteroids, and other solar system objects. But we are on the verge of something much more powerful. The Vera C. Rubin Observatory, a massive new telescope facility in Chile, is now beginning its operational phase. This telescope is designed specifically for wide-field survey astronomy. It will image the entire visible sky repeatedly, every few nights, building up a comprehensive and continuously updated map of everything in the solar system and beyond. The scale of its anticipated discovery rate is genuinely staggering. Within the first few years of its operation, it is expected to discover millions of previously unknown solar system objects. It will catch comets earlier in their journeys, while they are still far from the Sun. It will identify hyperbolic trajectories with more confidence and at greater distances. It will almost certainly detect true interstellar visitors faster and earlier, giving astronomers more time to study them before they pass through and continue on their way. What this means is that the discoveries that have excited astronomers over the past few years, Oumuamua, Borisov, 3I/Atlas, and now Wierzchos, these may be the beginning of a much more prolific era of discovery. Wierzchos is remarkable right now, partly because objects like it have been relatively rare detections, but as our instruments improve, we may find that they are not rare at all. We may find that the solar system is continuously ejecting objects and occasionally receiving them in a slow, cosmic exchange that has been going on since before the Sun ignited and will continue long after it dies. We are, in a very real sense, beginning to see the solar system as part of something larger, not an isolated island in space, not a closed system with defined walls, but a dynamic, open system embedded in the Milky Way, participating in a vast and ancient circulation of matter that spans billions of years and billions of miles. For those of us who have spent our lives looking up at the sky, there is something genuinely moving about that. The stars are not separate from us, the galaxy is not a backdrop to our existence, we are part of it, our solar system is part of it, and every now and then, something like Comet Wierzchos comes along to make that real in a way that the abstract numbers and diagrams simply cannot. Here is an ancient object, born in the same event that created Earth, carried outward by the gravitational influence of Jupiter in the solar system's infancy, drifting in the cold darkness for 4 billion years or more, then nudged by some gravitational whisper, perhaps from a star that passed within a few light years of the Oort Cloud millions of years ago, and set on a slow, curving path inward, falling for millions of years through the darkness, getting warmer, getting brighter, developing a glowing green coma, visible to people on Earth with a pair of binoculars, being studied by the most sophisticated space telescope ever built, revealing chemical fingerprints that speak of the early solar system's chemistry, and then, after this one brief encounter with the sun and with our awareness, continuing outward on a path that leads away forever, 4.5 billion years of history, one brief appearance, and then the long silence of interstellar space. As the comet continues to move away from the sun in the weeks and months ahead, astronomers will keep watching it. Every observation adds to the record. Scientists can track how the coma changes as the comet cools and the outgassing slows. They can monitor for any additional chemical signatures that might become detectable under different conditions. They can refine the orbital calculations to improve their understanding of exactly where this object is going. Each additional data point has value because opportunities to study an Oort Cloud visitor of this quality, under these conditions, with these instruments, do not come along often. In the longer term, we can expect that 2026 will not be remembered only for Wierzchos. Other comets are being tracked, the survey networks are working continuously, and with the Rubin Observatory ramping up, the next few years may bring a remarkable wave of new discoveries. Some of them will be ordinary, many of them will be interesting, and a few of them may be as significant as anything we have seen before. But for this moment, this comet holds the floor, this ancient fragment of our solar system's beginning, making its one and only close pass through the light before heading out into the galaxy forever. It carries chemistry that speaks of the dawn of our solar system. It moves on a trajectory that connects our small corner of space to the vast galaxy beyond. And it has been seen, measured, and understood more clearly than almost any long-period comet before it, thanks to instruments that our species built and launched into space within the last few decades. There is something I find quietly profound about the timing of all this. This object has been traveling inward for perhaps millions of years. It has been falling through the darkness for longer than our species has existed, longer than all of recorded human history, multiplied many thousands of times over, and yet it arrives now. When we happen to have the Vera Rubin Observatory about to come online, when we happen to have the James Webb Space Telescope in operation, when we happen to have the global network of survey telescopes that allowed Capsule Wierzchos to spot it and report it and give it a name. A few decades earlier, we might have seen it as just a comet, a pretty object in the sky. A few centuries earlier, we might have interpreted it as an omen, but now, right now, at this precise moment, in the long history of the universe, we have the tools and the knowledge to understand what it actually is, where it came from, what it is made of, where it is going, and what it tells us about the solar system and our place in the galaxy. That is, to me, one of the most remarkable things about living in this era of human history. Not the technology itself, as impressive as it is, but the alignment of the technology with the discoveries, the fact that we are alive and curious and equipped at exactly the moment when objects like this are being found and understood. Comet Wierzchos will not pass this way again. It is leaving our solar system for good. But it has left something behind. Not just data in scientific archives, not just images on the hard drives of astrophotographers. It has left a slightly deeper understanding of where we come from, what the solar system is made of, and how this small piece of the universe fits into something much, much larger. And that, I think, is exactly what the sky is supposed to do. Make us feel small in the best possible way. Remind us that we are not separate from the cosmos. We are made of the same stuff as that comet. The same ancient materials, shaped by the same ancient forces, moving through the same ancient darkness. And for one brief moment, in the great sweep of cosmic time, we had the remarkable privilege of watching each other pass.